Welcome to Lead Programmer. Today we are going to solve the question binary tree right side view. So essentially, you have a binary tree. Imagine that you're standing on the right side of it. You'll have to return the values that are visible from the top to the bottom. So imagine you are standing to the right side of the tree. You are able to look at the values um, of the binary tree. You notice we have one, which is like the rightmost value of that given level. We have three, we have four. So this is the first level of the binary tree. This is the second level of the binary tree. This is the third level of the binary tree. uh, when you notice the binary tree, you will look at the rightmost node of that level. So over here you observe 1, here you observe 3, over here you observe 4. So 1, 3, 4 is essentially what we have to return. So how do we solve this question? So one way is obviously a traversal. Now, what type of traversals do we commonly use? We either use a BFS or we use a DFS. In this case, what are we trying to achieve? We are trying to get the value of one node from each level. Again, this is one level, this is one level, this is one level. We want to explore all the levels and get the rightmost node value from each level. Now, how do we go through each and every level? Going through a level means exploring the breadth first, because going in depth might mean okay, going from 1 to a 2 and then 2 to a 5 and then processing 3 and 4 respectively. But that's not what we want. We want to first process 1 and then go to 2 and 3. We want to explore its neighbors before we go in depth. So that calls for BFS. Obviously, you can solve the question using DFS, but BFS would be an easier way to solve this. Uh, so the way I'm going to solve this is going to be similar to a question level order traversal, where we uh, essentially go level by level and print out all the nodes we see. The only difference over here in this question is we go through each and every level, we see the nodes at each and every level, but the only node we care about is the last node or the rightmost node. So that's what we append to the results array. So definitely check out the question level order traversal before solving this question, because those two are very similar, as you might notice here. Um, yep, it's a direct BFS implementation where we go level by level, take the rightmost node. So let's look at uh, this in action. So we have a code. So if the root is empty, we just return empty string. That's what is desired by the question. And we have a queue, as we do for BFS. And to that queue, we want to append the root. We also have a results array. That's what we return at the very end. We keep going till the queue is empty. So and then over here we have a size. We create a snapshot of the queue and we go through each and every elements for we go through those many elements, so size number of elements. So if we want to visualize this, let's say we take the example given. So in a BFS, our queue might look like this. So we first have a 1 in the queue. So that's what we append to the queue. So at this particular stage, we have a 1 in the queue. And then we come here, we take a snapshot, which means, okay, we see that the size of the queue is 1. And then we execute this particular loop one time. So there we first pop the element. So we pop this and we see if I is equal to size minus 1, which means if it is the rightmost element in the queue, then we want to append it to the result. So in this case, yes, it is. So we append 1 to the result. And we also see if the left and right nodes are not null. So if they're not null, we append to the queue. So here we append um, 2 and 3 to the queue. Uh, and that's it. The for loops as execution ends. And you might have noticed that the for loop pertains to the entire level, because that's what we create a snapshot of. Now we go back to our queue. We check, is the queue empty? No, the queue is not empty. So we move on to the next line. We take a snapshot of the queue, which means we keep track of the size. We see, okay, the size of the queue is 2. So our level contains 2 elements. We go to the for loop. We want to run it for 2 times. We first check that, is it the rightmost element? It's not, because I is not equal to size minus 1. So okay, so that's good. Oh, we also had to pop it. So yeah, we pop it, and then we see it's the rightmost element. No, it's not. We also want to append its children. So with the child of 2 would be 5. So we put that in the queue, and that's it. Uh, in the second execution of the loop, we see that I is indeed equal to size minus 1, because the size is 2. Uh, size minus 1 would be 1, and I over here is 1. So it is the rightmost element. So we put that into the result, and we add the children of 3, which is 4. And the story continues. We can take a snapshot. We execute 5. 5 has no children. Then we execute 4. 4 has no children, but 4 is the rightmost element. So we put that into the result, and voila, we are done. So after this, the queue becomes empty. So we break out of the while loop. So we break out of the while loop, and we return result. The time complexity would be linear, as well as the space complexity, since we use a queue. I hope you enjoyed it. Please subscribe to the channel. Thank you.